Okay, I've been solving Structly. I signed up for this course, and in parallel, I've been also solving um, this the same kind of set of problems, but in Swift. So I'll decided to start recording it. We'll see how it's gonna go. Yeah, that's it. So what I wanna do here is like I need to implement the merge list, and the first one that I'm gonna so this is somewhere in the middle of linked list course. So already did the like zip list, reverse list, get node value, linked list find, um, and I'll try to speed run it now. So the first one, merge lists. So I need to merge two lists based on the like. So this two lists have ordered values, and I need to kind of merge them together and return the head of the new list. So the idea how I gonna do that is to use a dummy as or like a sentinel value in the front. And then I'll do something like, so I'll have this, so let's say I have 1, 2, 3, and then I have like 4, let's say, and 7, let's say, and here we have like, say, 8. So this is, sorry, this is basically two lists I need to join together. This is like 8. That's okay. And how am I gonna do that? So the first thing I'm gonna do is I'm gonna create a tail, a new dummy node, and say the value can be -1 or like any value. Let's call it 42. So the value gonna be 42, and then initially gonna have like 2 pointers at head 1 and head 2, h2, h1, and then I'm gonna decide. I'm gonna look at the h1 and h2 and decide, okay, which of these has a lower value. And in this case, h1 has a lower value, so I'll touch it to the tail. It's gonna be 1. I'll move h1 pointer, so now h1 points at 2. And then the tail now also gonna point at 1, the thing that I just inserted. And this one is still gonna, I create the copy, it's gonna be dummy. And then as a result, I'll return dummy next. It's gonna be the output. So tail now is pointing at 1. And then again, like I have h1, h2, who is the lower? 2 is lower, so I'll attach it to the tail, and I'll move h1. And then I'll move the tail also here. So moving tail. And then again, I compare it. Like h1, h2, 3 is lower. So I'm attaching it, and I'm moving the tail here. So next one, and I'm also moving h1. So next one, h1 is pointing at 8, h2 is pointing at 4. So I just add 4 to the tail, 4 here. And then h2 gonna point at 7. The same happens again. h2 gonna point at, after adding it, I compare 8 and 7. 7 is lower, so I'm adding it 7. And then now h2 is pointing at null. Whenever h1 or h2 gonna point at null, I'm gonna exit the loop, and then I'll check whoever is not null, h1 or h2. h2 is null, so h1 is not null. So I'll attach to the tail whatever node is not null. So in this case, I'll attach 8, and then I'm gonna be the last null. And then I'll return dummy like arrow next, and this is gonna be the head of the new sorted merged list. So this one is the strategy here. So I'll create a dummy. So I'll have this node dummy let's call it also tail, is equal new node, and let's call it 42, and then node dummy gonna be equals tail, and then I'll have this while head1 is not equal null pointer, and head2 not equal null pointer. I'll do the following. I'll do tail. I'll check if head1 val is less than head2 value. I'll do tail next gonna be, let's call it less or equal. Tail next gonna be equal head1, and then I'm gonna have head1 gonna be equal head1 next, and I'll do the same for the head2 in case like head2 value is less than head1 value. I have tail next equals head2, and then head2 gonna be equal head1 next. Oh, head2 next in this case. And then I'll don't forget to move the tail. So tail gonna be equal tail next. And then in the end, I'm gonna have this tail next gonna be equal head. If head1 is not equal null pointer, then I'll do this head1. Otherwise, it's gonna be head2. And in the end, I just need to return. I just need to return a head, or like dummy next. That should be it. Okay. So other thing how to do that is to do recursive. Like let me like just summarize what I did. So I have a dummy. Dummy helps me with like even if those kind of null and this null, the dummy gonna point at null eventually, because head1 is null. I jump here, it's gonna be null, and then I'm gonna return dummy next, it's gonna be null. If either of them is null or other one is not null. So in this case, I'll instantly exit this loop, and then I'm gonna initialize it with whatever is not null. So tail next is gonna be whatever is not null, and then I'll return dummy next, so it's just gonna be one element. Or like not one element, might be like entire list, but like the other list is just null. So I'll just return the head of whatever list is not null. And if both of them are kind of not null, but maybe the same length or maybe different lengths, so I'm gonna like choose one by one, go through the nodes one by one, and like selecting whichever list has the lowest value, and I'll add it to the tail. And then like in the end, if the length of them is like different, like head1 or like list 1 and list 2, I just gonna add the remaining elements and decide what has a longer tail, which list has a longer tail, and just said the head is pointing at, it's going to be the remainder. So the next one is how to solve this recursively. Yeah, it was nice, solution, iterative, but like a little bit verbose here and there. The question is how I can solve it recursively. So let me think about that. So I'll do this something like if head1 is equal null pointer, I'll just return head2. Else if head2 is equal null pointer, I'll return head1. Return head1. Otherwise, I'll check if, so I'll call head1 value less or equal head2 value. then I'm gonna if this is true, can I assign the tuple? I wonder if I can assign the tuple. Local tuples in C++. Tuple. Yes, no. The answer is no. So just reassign it. So head one, if it's greater, then I'll do I'll need to do head one next gonna be merge lists, head one next, and then head two. Oh, if it's like less. If it's less or equal. Otherwise, head two next gonna be merge. And then here return head one. And then here I'm gonna be return head two. Okay, merge. Can I just call it like use a streak? If head one value is less than head, if it's like greater, then I'm gonna reassign. So I'm gonna be node head one, and then like temp equals head one, then temp head two gonna be head one, and then head one equals head two here, and then head two gonna be equals temp, and then here I'm gonna call head one next gonna be merge list head one, head two. And then return head one. Something like this. So if the so it should be if it's greater, then I'm gonna swap them. So this one should be it. Head one next here. Do you have permission? Do you have permission?
Yes. So his mom doesn't care. She's making a video now.
Zata, can you do your assignments?
Yes, after.
Here, head one next. Okay. So this worked. I wonder what if the poles head 1 and head 2 gonna have the null pointers. In this case, the head 1 gonna have equal null pointer and I'm gonna return just head 2 that's gonna be also null pointer. In case that head 1 is not null, in case head 2 is equal null, I can actually remove this else and do this head 2 is equal null pointer or yeah, even better here since I don't have to check, make another check here. Like it's interesting because like this seems like one-sided solution, but yeah. Let's listen what Alvin gonna tell us.
Hey, programs, Al here. Right now, let's go over the C++ walkthrough for this merging list problem. So this one's going to be a nice variation of our very last problem. Hopefully watch the approach to it first. What I want to do is teach you how to use the dummy head pattern for the first time. You're going to find this dummy head pattern very useful when it comes to constructing a linked list. So over time, I do want to merge together these two linked lists. I'm going to need some area where I can actually represent my output. So here's where your dummy node comes into play. Start by creating a node, and I'll call it my node, I'll call my dummy head. And it's going to just be like a fake node. So you actually don't want to store any like logical information here. I'll just put in some int value like 0. Really what's great about having like a dummy node is it lets you have a next pointer. Right? That way, my very first iteration of like my creation algorithm isn't like an edge case. Right? So now that I have this dummy head, I'm going to just tack things to the end of it. So I'm going to set up my current pointers like I usually do. So I'll say current 1, head 1. That'll be, of course, a node pointer. Say current 1, head 1. And likewise for current 2, head 2, right? Nice. Now I want to keep iterating while both of my pointers are not null, right? So while current 1 is not equal to a null pointer, and while current 2 is not equal to a null pointer. Nice. What I want to do is now start merging things, right? So they tell us I want to merge these two lists together in increasing order because they have integer values. So just do that comparison, right? Compare them. So if was not equal to a null pointer, and while current 2 is not equal to a null pointer. Nice. What I want to do...
I cannot hear him.
is now start merging things, right? So they tell us I want to merge these two lists together in increasing order because that's integer values. So just do that comparison, right? Compare them. So if we'll say current 1's value, what if it's less than the value of current 2? What I should do is take current 1 and add it to my list first. So to construct my merge linked list, I'm also going to need reference to a nice tail pointer. That way I can quickly add nodes to my result here. So I'm going to create another node pointer here, call it tail, and make that point at my dummy head. Notice that my dummy head is not a pointer, that's okay. I do want tail to be a pointer though. What's great about that is I can just take the value I need, which is the lesser value of current 1, and just add that to the next of my tail, right? So say tail next equals current 1. Now that I just consumed a node from current 1, I need to progress to current 1. So current 1 equals current 1 next. Awesome. And this else statement would just be the case where maybe current 2 has a lesser value, so that would just be... So I'm going to represent my output. So here's where your dummy node comes into play. Start by creating a node, and I'll call it my node, I'll call it my dummy head. And it's going to just be like a fake node, so you actually don't want to store any like logical information here. I'll just put in some int value like 0. Really what's great about having like a dummy node is it lets you have a next pointer. Right? That way, my very first iteration of like my creation algorithm isn't like an edge case. Right? So now that I have this dummy head, I'm going to just tack things to the end of it. So I'm going to set up my current pointers like I usually do. So I'll say current 1, head 1. That'll be, of course, a node pointer. Say current 1, and represent my output. So here's where your dummy node comes into play. Start by creating a node, and I'll call it my node, I'll call it my dummy head. And it's going to just be like a fake node, so you actually don't want to store any like logical information here. I'll just put in some int value like 0. Really what's great about having like a dummy node is it lets you have a next pointer, right? That way, my very first iteration of like my creation algorithm isn't like an edge case, right? So now that I have this dummy head, I'm going to just tack things to the end of it. So I'm going to set up my current pointers like I usually do. So I'll say current 1, head 1. That'll be, of course, a node pointer. Say current 1, head 1. And likewise for current 2, head 2, right? Nice. And I want to keep iterating while both of my pointers are not null, right? So while current 1 is not equal to a null pointer, and while current 2 is not equal to a null pointer. Nice. What I want to do is now start merging things, right? So they tell us I want to merge these two lists together in increasing order because they have integer values. So just do that comparison, right? Compare them. So if we'll say current 1's value, what if it's less than the value of current 2? what I should do is take current one and add it to my list first. So to construct my merge linked list, I'm also going to need reference to a nice tail pointer. That way I can quickly add nodes to my result here. So I'm going to create another node pointer here, call it tail, and make that point at my dummy head. Notice that my dummy head is not a pointer. That's okay. I do want tail to be a pointer though. What's great about that is I can just take the value I need, which is the lesser value of current one, and just add that to the next of my tail, right? So I can say tail next equals current one. Now that I just consumed a node from current one, I need to progress current one. So current one equals current one next. Awesome. And this else statement would just be the case where maybe current 2 has a lesser value, so that would just be symmetric, right? Then set tail next equals current 2, and then progress current 2 to its next node. Awesome. And as I perform this algorithm, I also want to make sure that at any point in time, tail points to the last node of my resulting linked list. So no matter what node I add to the end, always set tail equals tail.next. It's really important that you do this step over here because you need to get ready for the next iteration because you're going to append another node. Awesome. So that's going to be my main algorithm. It has a very similar shape to our zipper list problem. Instead, now you do it based on a comparison, right, which node you take. We're also utilizing our very clean dummy head pattern, right? And so what I want to do is, after this while loop is done running, that means one of my linked lists emptied out, right? And if one of them emptied out, the other linked list might still have some content in it, right? What I want to do is just take all the remaining elements and add them to my output. So just like we did in the last problem, I'm going to check, let's say, what if current 1 has leftover? So if current 1 is not equal to a null pointer, I can just take all of those nodes and add them to my tail. So just say tail next equals current 1. But it might also be the case afterwards, what if current 2 has leftovers? Then set tail.next equal to current 2. Awesome. Now how can I return my final answer? Well, because I created my nice dummy head, I really just want to return the node that comes after my dummy head, right? It would be incorrect to just return your dummy head, because you really don't want to return that as part of your answer. You only use this dummy head for the sake of its next pointer, right? So I can say dummy head dot next here. Watch out for my C++ programmers. The reason I'm using a dot here and not a skinny arrow is because dummy head is not a pointer, right? It's actually like a variable. So let's go ahead and give us a test run. A lot of stuff going on here. Be sure you watch the approach video, right? Give that a test run. Also, you're going to get a little typo. It's telling me that I can't convert a node to a node pointer, and that's because when I initialize my tail over here, like I just said, right, dummy head is actually a node. I can't store a node within a node pointer. Instead, I want the address of that node, right? So just use the ampersand here. It's a classic C++ bug there. Let's get that test run now. Awesome, there's a solution iteratively for our merge list problem. All right, so that was the iterative solution. Let me show you how you could solve this one recursively, of course. Looks like to solve it multiple ways. So it's going to be really the same spirit of a solution. We'll just start with our base cases. Hopefully you remember our last recursive zipper function. So I know if one of my lists empties out, then I just want to return the other one, right? So I'm going to need two base cases here. So I'll check if head 1, let's say that is null pointer. I just want to return head 2, right? Because there's nothing else that kind of merge together. Just return the remaining content. In a similar way, it could be the case that maybe head 2 is null, in which case I return head 1. So those are going to be my two base cases. What I want to do now is actually perform the merge, right? So if I make it past these if statements, I know that head 1 has a node and head 2 is also a node. What I want to do is compare them, right? So I'm going to check, right? Maybe head 1's value, maybe that's less than head 2's value, right? And if it is, then I know head 1 should appear first, right? So what I should do is have head 1 and begin to set its next over here. What I want to do is set its next to the remainder of like the merge list. And to calculate that recursively, just call your function, right? I can do merge lists, pass along my head 1 next, pass along my original head 2. So you're probably wondering about this recursive call here, right? So why am I passing in my recursive call head 1 next? Well, I just used a node right now from head 1, right? And so I need to look at the next node recursively. The reason I don't say head 2 next over here is because I didn't take head 2, right? Because head 1 was lesser. Good. In terms of how this recursion works, hopefully you understand whenever you make an assignment like this, you would be evaluating the right-hand side first, right? So I don't really need a temporary variable here if I don't want to, right? So I'm going to recursively merge together head 1's next with head 2, and then whatever node I get back, representing the head of that merge list, I'm going to set that as head 1's next. And I just do something very similar for the other side, right? So in this case, that means head 2 is a lesser node, so it should come first, and it should connect with the remaining head. So I pass along the original head 1 here, and then head 2 next over here. Awesome. And now for both of these if else statements, of course, I need to return a pointer to a node. So in this case, head 1 was the head, so return head 1. In this case, head 2 was head, so return head 2. That's how you might solve this one recursively. Feels like very similar in structure to our iterative version, right? Just using some recursive calls now. Let's go ahead and give that a test run. Typically, because we're doing this recursively, you actually don't need a dummy head pattern. You just have to utilize some very wise return values, right? The key to victory for a recursive linked list problem like this one is to understand that your recursive function is going to return the head of that merged linked list. Let's give this a test run. Cool, and there we have it.
Okay, makes sense. Solutions, merge lists. Okay, makes sense. Let's see. Okay, let's go to the next one. Pep talk.
Hey programmers, I want to take a little break from our linked list module to offer some words of encouragement. Those last few problems were tough. Don't get down on yourself if you found them challenging. Like I told you before, I really expect you to have to use the approach and walkthrough videos to solve these for the first time. It's not a failure if you use the videos. Here's what really matters. The thing that matters is what you do after watching the videos. You should reattempt the problem and see how far you get. Hold yourself accountable. Maybe take a 15-minute break, then reattempt the problem. Reattempt it tomorrow and the day after too. See how much you can remember. Going back to previously completed problems is a great way to learn. And at any point, if you get stuck again, that's totally fine. Use the videos to unstick yourself. Every time you get stuck and use the videos to get unstuck, you are getting better. It precisely highlights the mistake you made and helps internalize how to avoid it in the future. Be willing to make the mistakes now, because if you make them now, you won't make them in your interviews. So don't be too hard on yourself if you're not solving things perfectly. If I can give you any advice on data structures and algorithms, or even just software engineering in general, don't focus on being perfect, focus on getting better. All right, let's get back to it.
Okay. If univalue list is univalue that may takes a pointer to the head of a linked list as an argument, our function should return boolean indicator whether the linked list contains exactly one unique value. False, true, false, true. Okay. How I can solve it? Uni-value list. Let's call it uni-value list. Call it copy previous task. Merge lists. What was here? Merge lists. And then I've had the previous one. That's basically tail dummy. Is it the same? Yeah, it's the same. Here. Okay. So we have this included now. So the next one gonna be a uni-value list. So here what we have uni-value. So recursive solution should be pretty straightforward, I would say. So I'm thinking right now how I can like do that recursively without modifying this API. So all I want to know is like head if head is equal null pointer. If head is equal null pointer, I'm gonna return false probably, and then otherwise. Otherwise, I'll do easy value list. Okay, new empty file is uni value list. So plus here. Okay. So if head is null pointer, return false. Or maybe even yeah, I don't see how I can do that without. Okay, whatever. I'm gonna just pass create a helper function. Is uni list. Then I call it node, and then int val, and then if node is equal null pointer, I'm gonna return true, and then return node dot val is equal val, and is unilist, and then here node next to val, or like, yeah, val. And then I wanna call it from this return is unilist, node next, and then node val, or like head next, head val. Let's see if it's gonna work. Okay, yes, upper. Where is it? Not val. Okay. Okay, how can I do that? Somehow recursively. I can eat it up, like remove the list completely, kind of. Can I do that without this additional function? So I need to check. If head is equal null pointer, I need to return just what was I was doing here? Return to, okay. If the head head is equal null pointer, I guess return true, and then return is value list head next and oh. Yeah, interesting. How to do that without like changing API? I don't know. Let's pretend It's only. Let's try the what? The working one was this one. Is union value list. And then iterative solution gonna be unordered. The unordered set. Here integer. Wow. We'll have this node is equal head. So while head not equal now, or like node, then I'll do set dot append, I guess, node wall. If set dot count greater than 1, return false. Otherwise, I wanna do what? Node equals node next, and then in the end I wanna return true. So here let's include unordered set. So here null pointer. S add. No. Insert value in unordered set. See, oh, insert. Where I was I? Oh, I was here. Insert. Is it like this? My set, okay. Insert. Should work. Okay, let's try to solve it here. Inca boot. Yoo-hoo! So this one was a recursive solution. Let me check what the approach.
Hey programmers, Alan here. Right now I want to go over the approach we can use for this is univalue list problem. So in this problem, our input is going to be a linked list, and what we want to do is return a boolean indicating whether or not the linked list contains only a single unique value. So for example, if I look at this particular input, notice that every single node contains the same value of 7. In other words, there's only one unique value within this linked list. So in this scenario, we should return a true, right? This input list is indeed a univalue list. Let's say we had another example. Looking at this other linked list of 2232, if we wanted to figure out whether this one is univalue, the answer would be false, right? Because we don't have only a single unique value within the linked list, right? We have 2s, but also a 3. So how can we come up with a strategy for this one? Let's step through this particular example. And so this problem's pretty straightforward. What we could do is adopt an iterative approach. We know that we're going to be given the head of the linked list, and we know that the only time we should return true is if the head's value is the same as every single node's value within the linked list. And because of this, we always want to reference the value of the head. So I'm going to mark that over here. I know the head value is 2. Now, if we just begin our classic linked list traversal, we're going to start our current at the head node. And what I can do is just simply check, is my current's value equal to the head's value? And if it's true, then I can continue looking through the rest of the linked list. I know that if I have access to current, by doing current.next, I can move to the next node sequentially. And I ask myself the same question. Is my current's value the same as my head's value? That's true, so I continue. Finally, on this iteration, I see something's wrong, right? If I check if current's value is equal to head value, that's actually false. And because I just found something that is not the same as the head, then in this scenario, I can just immediately return false for my function, right? This entire linked list is definitely not a univalue list. And so overall, we're going to need to encode some logic that says if the head's value is not equal to the current's value, then return false. That being said, where should we return true? Let's say that we amended this example. So maybe instead of a 3, let's say I made this actually all a bunch of 2s. So I'm changing the example over here. And so now it would be the case that this node actually passed because its value is the same as the head. And when I go on to the next iteration, that's also true for this tail node. And when I get to the very end of my linked list, I know that current would be set to null. And I think at that point, if ever I finish iterating through my entire linked list, then I should return true. Because if I didn't find any mismatches, then it must be the case that the entire linked list is indeed containing a single unique value. In other words, we need to encode some logic that says if we finish traversing the entire linked list and we never find a mismatch, then simply return true. And that's pretty easy to code up. When it comes to the complexity analysis of this problem, let's say we solve it in exactly this iterative fashion. We'll say that n is the number of nodes. We know that we just traverse through the entire linked list, so we need a loop that has n iterations, right? An iteration for every node of the linked list. Our space complexity here appears to be just O of 1 constant because we're not storing any arrays or anything like that. We just have a constant number of variables. So this actually looks like a maximally efficient solution we can use for this univalue problem. So what I want you to do is give this problem a shot on your own, try to code it up, and if you get stuck, I'll catch you in the walkthrough videos. See you there.
Okay, let's walk through.
Hey programmers, Alan here. Right now let's go to the C++ walkthrough for this is univalue list problem. So if we watch the approach first, we'll jump right over here. I'll show you how to solve this iteratively to get going. So what I'll just do is start by implementing my core linked list traversal pattern. So what does that mean? Well, I'll set up a current pointer. So that'll be just a node pointer, right? Initialize to the head like usual. I want to keep iterating while the current pointer is not equal to null pointer. If I just traverse through the linked list, all I need to do is set my current equal to current next. Awesome. And so in this problem, I do want a Boolean return type, right? I want true if every value within the linked list is the same, false if they're not all the same. So what I can do is really just compare my current node's value against my head value, and they should always be the same. In other words, if they're different, so if current val, if it's not equal to head val, then I know I have a difference, and so I should return false. Right? On the flip side, where should I return true? Well, that should definitely be after the while loop, right? Only after you check the entire linked list and you find no difference, then you can say true, everything is the same value. So there's a nothing fancy solution for this one. Let's go ahead and give it a test right now. Like we expect, this is going to have a linear runtime, right? Because we have a while loop, just iterating through every node of the linked list. The space complexity is going to be constant. So let me show you how you can also solve this pretty easy problem using some recursive code.
So what he does here, current value not equal head value. Okay, that makes sense. So compare everything with the head. Instead of like creating the set, then I'll do this if node So if node val noded, if node val headed noded, if node val not head val not equal, if it's val okay, if it's not equal node val, then return false. Then if the head is equal null pointer, is node is equal null pointer, then return true. Okay. Will it work? Node. Head was not declared in the scope. Let me pause it. Okay. So here, if the node pointer head value okay. So basically it's the same here. I was solving this. Okay.
So let me show you how you can also solve this pretty easy problem using some recursive code. And I think no matter how you kind of solve this one recursively, it would be wise to split this into a main function and a recursive helper function. Right, so this will be my main function, and above it, I'll define the recursive helper. Because like we did in the iterative version, we're going to need to refer to not only like my current node, but also the head node. So maybe I'll create this as current, and also taking a pointer to, we'll say my head node, which we find over here. And all I need to do is do the traversal and just check for a difference once again. So if I look at the main function here, how should I call my main function? All I need to do is invoke is univalue list, given the head node twice. Right, the first argument's like the current node, the second argument's always going to stay as a reference to the head. Right. So now in my recursive function, I can just lay out some nice base case here. So let's say if my current node, so current, what if it's the null pointer? Then I need to return some value here. It would be wise to return the true boolean, because that means I made it through the entire list, right? Now on the flip side, I can check, all right, what if my current node's value, what if that's not equal to my head node's value? Well, then I should just return false, right? I don't need to iterate through the rest of the linked list. I can just return false. But let's say that my current node's value is equal to the head value. Well, then I want to just keep iterating through the rest of the list and verify those remaining values. So here I'm just going to call my function is univalue list, pass along current next over here, and I'll keep head the same. Head can always reference the first node of the linked list. That's not too important here. And I know that this call is going to give me back a boolean. Whatever boolean next is back, I'm also going to return upward. So it's going to be a nice recursive solution for this is univalue list problem. It's going to have a linear runtime, but also a linear space complexity. So we have a little typo here. Missing an I seems, just like so. Let's run that back.
Okay. So what he was doing, null if node is equal null pointer, return true. Okay. And then if the node val equals head val, and then it's unilist node next, and then here head. Yep, something like this. Let's try it out. Yep, that's working. Okay, so how to do this in Swift? Let's say building for macOS is but linking with the lib. It was built for a newer version. Okay, shall I upgrade the macOS version? Let's do it knows that I'm building for macOS 13. macOS. Okay, can I do just go? Let's search it in Gemini. I have what? I have package Swift. I have package but Swift and need to support 2 platforms. Mac OS and Linux. Okay, platforms, targets, platforms, products. Ah, okay, 14. Let's change it. Yeah, no warnings anymore. No, still. What if I change it to I have following file? Okay. Will it work? No. But even if I change to 14, platform for 14, it still doesn't go away. Oh no, it went away. Okay. And then let's say test. Okay. Hmm. Okay, everything should be working. Sources directly. With the interoperability. I don't know why this is so. Now using Magazine. Structy. So this one. Okay. Okay, whatever. So I need to solve this uh, linked list is uni-value list for the Swift. Let's write it down. Is uni-value list. And then for the tests, I wanna do is uni value list test. I have somewhere here the folder with already moved tests. Okay. And then here, if let's call it is uni value list. And let's move this function to here. Is uni value list. And then here I wanna do import and substitute everything here, and then here. Okay. Test failed. Expected because I have not implemented it yet. Doesn't show up here. No. Let's call it test suite 4. And then is new value tests. Any value list tests. Doesn't show in this list. 0.4. No, maybe I need to refresh the Xcode. So I need to implement this function. Then I need to check. So I'll have this if head, if guard, let head, else, return true, and then otherwise I'll go var node t equals head, and then wow node dot val while let node node equals node next, say current equals node equals current next, and then here if node current val not equal head val, I'm gonna return false. And then if I manage to go up to the end, return true. Okay, let's test it. Okay, now test this passing. Here everything is green. There is no test for empty values. Let's do test 6. If I have if I pass just nil, okay, return should be true. How about that? Test 6. So like let you node int I equals nil, and then you Hiyazata. Okay, that's passing. Let me commit it. Okay, status git add git commit Structy tasks git push. Okay, let's watch next episode. Approach walkthrough. Okay, I guess I will
verify those remaining values. So here I'm just going to call my function is univalue list, pass along current next over here, and I'll keep head the same. Head can always reference the first node of the linked list. That's not too important here. And I know that this call is going to give me back a boolean. Whatever boolean next is back, I'm also going to return upward. So it's going to be a nice recursive solution for this is univalue list problem. It's going to have a linear runtime, but also a linear space complexity. So I have a little typo here. Missing an I seems just like so. Let's run that back.
So, wonder what this microphone is. It like a good one? Whatever. So solution. So this one is iterative solution. Just storing the head and then checking the current with the head and then moving current. And this one is like a recursive solution, just comparing current with the head. And then if it's equal each other, just move current to the next list element. Okay, let's go to the next one. Pointer to the head of the linked list as an argument. The function should return the length of the longest consecutive string of the same value within the list. Okay, we have 557776. So how to do that? Okay, let me make a pause. Drink a little bit coffee. Okay, resuming this one study session. How I can solve it in C++. Longest string. Okay. Copy here. Oh no, copy here. So let's call it longest streak C++. So we should return, I should return the true, and then I'll have this node, so let's say res int res equals 0, and then node is equal head, and then while node not equal null pointer. I'll check if the previous value so it can be any integer. Let's call int val equals 42 initially, and then if node is equal head, I'll just go and let's say we have int counter is equal 1 or like 0 initially, and then I wanna return res here, and then if node is equal head, then val gonna be equal node val, and then counter gonna be equal 1, or here if the node val not equal val, counter is that, and then like res is equal max, is it like that? I don't know, max, and then counter, then press account and counter, and then I'm gonna set the counter, else I can just increment the counter, and then in the end I wanna update the res. Res is gonna be the same max between res and counter. And then I wanna know how to do math. So I guess it's include math, and this max. Is it C math? Max? Yeah. Okay. So this one should work probably. Max math, not max. Okay, I don't remember how to do max. So C++ max function. Algorithm, what? C++ max function. std max. Okay, algorithm, okay. Well. This one is algorithm. Okay. Include algorithm, and then here I'm gonna be max standard max, and then here standard max. Okay, this should be it. Okay, let's try it out. Test. Include. Include. Node. So here, forgot to move the node. Goes node next. Yeah. So let's do the recursive solution in Swift. New empty. How to say that? Longest string. And then here, empty file, longest string tests. And then here I'll import the testing. Then here test suite longest string tests. Okay. Let's copy. Copy paste. Have some change to this. Longest string, longest string, longest string, string, longest string. Okay. So now I'll try to test it. I'll move this one function into longest string. And let's try to test it. If it's gonna be successful, obviously no. What worries me here is that it doesn't show up the, shall I just restart? Yeah, I should just restart it. And then it will upgrade it. So here I'll call it longest string tests. Let's call it suite. Longest string test suite. Let's call it tests here. Okay. Okay, I wanna test it. Let's run it. Okay, failed. Here, failed. Okay, time to implement them. Go here, then towards the longest string. So here I wanna do something like so I want recursive. For this I need a global var longest string count goes here. Interesting. Yeah, I'll probably use the internal function. So I'll have this func longest function longest. Then it will accept it. Okay. then I'll do something. Okay, T is declared. Okay, let's do this. So I need node here, node, and then I need to have val in out integer, and then max frequency in out integer. Or like car frequency. How to do that recursively and like do that efficiently recursively? So obviously I need to compare so if node is guard node guardlet node, else return say counter, return counter, and then node is not none, new. So I will do if I just return 0 here, and then I'll have here somewhere outside, I'll have this int var global max equals 0, and then I'll do if say node val is equal node next val, and then if this one condition holds, then I want to do return 1 plus longest node next, then I can skip probably this one. So let's call it var res equal 0 equal 1, and then res plus equal or like it can be like 1 plus, else it's gonna be res equal so here global max always gonna be 1, so 1, so I should reset it, yes, equal 1, and then I'll do this global max equals max global max, and then the res, and then return res. It's a little bit verbose, I don't really like it. So let's check if I wanna return longest head counter, the need counter. So longest head So I'll call it longest head, and then I'll return global max. So this one can be simplified up to this one plus longest node next, or otherwise just one. Yeah, something like this. So let's try it out. No. Poo, 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 poo. It says max, global max, and then longest head. No, then it's not. Result 2, expectation 3. Where I missed it. So if the node is null, I'll return 0. If the node val is equal node val next. I don't go further. Well, I should be doing that no matter what. So I'll do that. Something like this. Let Raza call this. If node val is equal node next val, I'll go res plus equal 1. Still no. Oh. So the conditions global max is 0. Now we have only 2 test failures. 2 and 1. Okay, so res by default should be 1. And then var double, like next res is equal longest. And then if the it's called res, then next res equals 1 plus next res, else res is equal just 1. So var res is equal 1. Okay, so now how I can simplify it? Equal plus equal, well, if it's like equal to each other, I'm gonna do next res otherwise 0. That's code. Look ahead length. Actually, I can return the tuple. First tuple gonna be global max int, and then I'll return okay, something like this, and then I'll do res, and then res global max equals longest head, and then I'll return global max, yeah, global max. Return 0, 0. Apply that. It's here. Apply that. This is recursive solution. I don't really like it. How I can optimize it? Okay, let's do this approach.
Hey programmers, Alan here. Right now I want to go over the approach we can use for this longest streak problem. So in this problem, what we want to do is take in a linked list as input and return the longest consecutive streak of the same value inside of this linked list. So if we take a look at this input, there are a few different streaks we could consider. One thing to bear in mind is we must have a consecutive streak. So that means adjacent nodes need to be the same. One streak I could find would be this 5, 5, and that would have a length of 2. So that's one possible candidate. Another streak would be these 3 7s in a row with a length of 3. And technically, a very, very small streak would be just this lone 6 with a length of 1. So between those 3 streaks of 2, 3, and 1, I want to choose the biggest one, which would be length 3, representing those 7s. And so how can we go about solving this one? Just looking at the mechanics of what they're asking, it seems like we need some max value logic, and obviously we also need to traverse through the linked list. What we can do is just just maintain a few key variables. So let's walk through how this can work. I know in the long run I want to figure out what the max streak is. I can initialize some variable starting at 0, which is kind of convenient because let's say we were given empty linked lists, then technically the max streak would be 0. So in addition to a max streak, I know I also need to track my current streak, right, the current streak I'm on, and I'll build up that number by incrementing it as we go. In addition to that, I also need a way to check for consecutive values that are the same, and I can use a previous value variable. And by default, I'm going to assign this basically as empty, so either use null or none, whatever your programming language affords you. And so when I get the ball rolling on this, of course I'm going to use a current pointer to point at the head of the linked list. And I'm going to use this to traverse throughout the entire linked list. But how do I start this algorithm? Well, what I should do is check, all right, my current value is 5. I should compare it against my previous value that I have stored. Technically right now, this is empty, so this can be a special case. I should just take my current value of 5, store it in that previous val variable. At that point, I just began a new streak, and so I should increment my current streak and set it to 1. And technically, as soon as I see any node, that would be a streak of length 1. And as soon as I have current streak as 1, at any point in time during this algorithm, whenever current streak becomes greater than the max streak, I should replace the max streak with that value. So technically, so far, my max streak is 1, and also my current streak is 1. At this point, I can set current to current next and look at the next node sequentially. And what I should do is take this current value of 5 compared to the previous value I've stored. Since they're equal, that means I'm extending my current streak. I'm extending it with another node, and so I should increment current streak.
Okay, let's copy this one. If it's more explanatory, I'll just check here. Let it run. I don't have tests for this one. Let's run it here. Okay.
By 1, so now current streak is 2. At this point, my current streak is again greater than the max streak, so the max streak should be reassigned as well. So far, the max streak is 2. Next iteration, we're at the 7 node. I compare that 7 to my previous value of 5. This time around, they're not equal. So if they're not equal, I must be breaking a streak. So I need to reset this current streak variable down to 1. And the reason I set it to 1 is, well, I'm at a 7 node right now, and that's exactly 1 node. If you reset current streak down to 0, then you wouldn't be counting your current node, so you would have a small count, a little off by 1 there. What I also need to be sure to do is not overwrite max streak, right? So whenever current streak gets reset, I should not change max streak, right? At any point in time, max streak needs to represent the length of the longest streak I've seen so far, which is still 2. At this point, I can also update previous value and now set it to 7 for my future iterations. Next iteration, I move on to the other 7, and I see that, all right, this value is equal to my previous, so I increment my streak. My current streak is 2 and my max streak is 2, so nothing happens here. I progress to my next node. Again, I have a 7. My current value is equal to my previous value, and so I increment my current streak to 3. At this point, my current streak is bigger than my max streak, so I replace the max as 3. Next iteration, current is 6. I compare that 6 to my previous value of 7. They're not equal, so I reset current streak back down to 1. And at this point, I can also reset my previous value to have this 6. And on next iteration, I actually hit the end of my linked list. So we're going to have some classic code that says, once our current pointer hits null, we're just going to exit our loop. And what do you know, if we look at our max streak variable, it does indeed hold the correct answer. So that's a pretty straightforward algorithm. What can we say about its complexity? If we say that n is the number of nodes in our input list, we can say that the time complexity is just going to be O of n, because we're just iterating through every node of the linked list and traversing through it exactly once. The space complexity for this algorithm would also be O of 1, because we only need to store a handful of variables. We're not creating any arrays or strings or anything like that. All right, so this looks like something we can code up. What I want you to do is try to code up this algorithm on your own, create those variables that we mentioned in this approach video, and if you get stuck, you can find me in the walkthrough video. I'll see you there.
Okay, let's watch walkthrough.
Hey, programmers, Alan here. Right now, let's go over the C++ solution for this longest streak problem. So we'll jump right in. I think the best way to solve this one is to write some iterative code. Like we said in the approach video, I'm going to need a handful of variables here. So definitely baseline we're going to use is, of course, our classic linked list traversal pattern, which means we're going to need some current variable starting at the head. And I want to iterate while current is not equal to the null pointer. So let me get the kind of classic code out of the way here. Set current equal to current next. But beyond that, I'm going to need a few other variables, right? I know in the long run I want to return a number, right, representing the length of the longest streak. So I'm going to create an integer variable for that. So I'll say longest over here, set it as 0. And along with that, I'm also going to need to track the current streak I'm on right now. That'll also be an integer starting at 0. I'll call it current streak. Maybe here I'll be more specific. I'll say longest streak. And along with that, how can I even consider myself on a streak? Well, I need to know what my previous node was. So I can look at its value inside. So I'm also going to store another node pointer. I'll call it previous over here. And because at the start, when I set current equal to head, there's nothing previous to the head, so I'll just set previous to the null pointer. It's a good default value over here. So how does my algorithm flow right now? Well, what I want to do is check if I'm extending a streak, right? So what I'll do is I'm going to go ahead and check, what if my current node's value, what if that is equal to my previous node's value? If they're the same, that must mean that I'm increasing a streak, right? I'm currently on a streak and extending it. So I should increment current streak by 1. Awesome. On the flip side, if my current value is different from my previous value, then I just broke a streak and I need to start all over. So I'll hang out with an else statement here. Otherwise, I should set my current streak back down to 1, right? If I'm breaking a streak, I set it back down to 1 because I'm counting the value of my current node as 1. It'd be incorrect to put a 0 here. So I need to be not even counting this node, right? So you set it back down to 1. Awesome. Something you may immediately notice, especially looking at this condition, this code would only be safe if my prev pointer is not the null pointer, right? Because I can't say null pointer val, right? So really the first iteration in this while loop is going to need to be like a freebie for us. So what I'll do is just use an OR statement, and I'll say, all right, automatically increment by 1 if your previous is the null pointer. Good. Because I know that in the first iteration, this is definitely going to be true, and I just enter the if statement. I don't evaluate the rest of this. So nice short sort of evaluation in C++. Awesome. So that should form the logic that helps me increment a streak as well as break a streak, resetting it to 1. What I also want to do is work in like the max value logic, right? Finding the longest streak really means finding the maximal streak. So what I'll do here is just go ahead and check what if my current streak, if it becomes larger than my longest streak, then I can just replace that longest streak, right? So say longest streak equals current streak. Right? So kind of a separate piece of logic over here to find like the max over here. Now beyond that, the only thing I need to consider is updating previous properly. So when I move to the next node, that means current equals current next, and really I should say previous should be the current, just shifting my point of view here, right? And after my while loop's done running, when I hit the end of the linked list, I can just return the final value that's inside of my longest streak. And this should implement exactly the strategy we spoke about in the approach video.
So what he does, okay, current not equal null pointer, that's condition of exit, initial longest 0, current 0. And then while pointer at current not null, he checks if previous is equal null pointer or current value is equal current, then so this is condition for start. So I have this is in my code. But if here, okay, if node and previous node val not equal previous, so this is reversed, and I'm just updating it in a loop, but he does it in here. He also updates it in a loop just outside of if statement. I can avoid doing all this last minute like this, and then skip this one and then return. Should pass, yeah. Let's copy this one into my solution. GGG. Not all that better. Like I don't need to do extra reassignment in the end.
Video. So definitely a few moving parts here, but notice how nothing here is too novel in itself, right? We definitely know how to just iterate through, linked lists. We also know how to do some max value logic. I guess the only new part here is tracking a current streak over time. Let's go ahead and give this a test run. Awesome, and there's a solution for the longest streak problem.
Okay, so what's the next one? Which problem? Let's make it smaller. Course content. Linked list, multiple choice. Okay, linked list, multiple choice. What's the commonly used to describe the first node of the linked list? Head. Then for target value in standard. Okay, off and time. Off one space. If you do it iteratively, yeah. If recursive solution, then it's gonna be off and due to this stack. Why might the expression current next val be unsafe? Current next might be the null pointer. Yep. What is the name for the pattern where fake node is used? Dummy head. What do properties? I typically store in value and next. Yes. Okay. So next task. Remove a node. So in C++, how I can remove the node with the video length already. I've been solving it for like almost 2 hours. That's interesting. So remove node. Write a function remove node that takes a pointer to the head of a linked list and a target value of the argument. Function should delete the nodes containing the target value from the linked list and return the head of the OK. Your target appears multiple times, only remove the first and so OK. So doing that fast. Let's do that fast. Remove node. So I'm gonna have this create a dummy node. Node. It's called dummy equals new node 42, and then then dummy next gonna be equals head. Oh, target value. So let's go full bar, another one, and here while, so like prev node prev gonna be equals dummy, and then while head, oh like let's say head not equal null pointer, and check if head val is equal target value. I'm gonna go prev next is equal head next, and then break, but then here head is equal head next, and then in the end I'm gonna return, that's a trick, return dummy next. Okay, let's test it. Head val equals target value. Head.
So here we are returning a C.
Of course. Prev equals head. Next task. I don't want to spend some time here and there. Insert node. Now we are inserting the same. The function should be insert node with a value into the list of the specified index. Okay, so we're gonna have this. It's called node again dummy, all accent now. Dummy equals new node is equal full bar, and then dummy next equals head, and then counter call in counter equals 0, while counter not equal, while counter less than index, I'm gonna have head is equal head next. It can be like greater than the length. Now it's called and head not equal. That's fun. So JavaScript. That's fun. Not equal null pointer. I'll do this reversal, and then let's go if head is equal null pointer. I'm gonna go return null pointer as an error. Otherwise, I'll do something really bad here. So I'll do counter increment, and then I'll do head. Okay, so like previous node previous equals dummy, and then here head equals head next, and then previous equals head, and then I'm gonna do previous next equals new node So node new node equals new node with value, and then I'll do previous next equals new node, and then new node next equals head. And then I'll return dummy next. This one for the insert. Next task. Oh, let's do this. What is the optimal complexity we can achieve for searching target in a standard linked list? Often. Okay, and often time of one space. What is dummy head pattern for linked list? Okay, when we attach the proxy or like new node to the head of the list, that helps us to avoid additional checks for the nulls. Okay, what is a commonly used term describe the last node of the linked list? Tail, already watched it. Okay. What two properties are typically stored in value and the next? And what term is commonly used to describe the first node? Okay, head. Why might be expression current, next, and save? Well, I already answered that because the next might be null pointer, and the val will trigger like null pointer dereference. Okay, so let's watch what Alvin question. Okay, next one. Hello.
All right, programmers, now let's run through some linked list problems. We utilize time and time again a traversal algorithm, which could be implemented recursively as well as iteratively. We're going to have more opportunity to practice linked list problems later on in the course, but I think for now it's more important to switch a topic. That way we can do some deep recall later on.
Okay. The linked list, the next one linked list will be about palindrome, middle value, cycle, unduplicate, sort of linked list, create linked list, build a queue. Okay, that's interesting. NQ and the queue. So like we have head and tail here. So NQ will be something like head, tail, null pointer, queue. Get size NQ. So I should define where I will add it. I'll add it to the tail. So like a queue, I'll add it to the tail, a new element, and the queue I'll take it from the head. So the NQ will be tail. So I'll have this node tail next equals tail next. So here I'll link the tail tail. I thought that it's double linked list. Okay, tail. So it's queue, it's not deck. Okay, tail. Oh no, build a queue. I thought that this Structy was gonna have like high level build a queue. What the linked list, so it's 12. Let's create new empty folder, 12 linked list 2. So let's do new build a queue, empty file, build air queue, ooh, C++. Okay, so here guide. So here I'll do this head. No, why? Node. Let's do head and tail gonna be sentinels. Node, and then in C++, how we can do it initial default value like this, node, and then tail gonna be also node, and then I'll do head like tail dot. So like I did like the head. Okay, what? What is the head of linked list? It's where we insert, yeah? Entry point of without there is no way you can locate any. What is the head? Let's refer to the node. Okay, head is just the end, tail. So we should the queue from a tail. But if it's like not double linked list, I'll need to. So the enqueue will be to the head. Head next equals tail. Okay, head next equals tail. Head next equals tail. NQ, so tail next. Okay, and then new node equals new node all, and then node next equals tail next, and then tail next equals node. So I don't need tail next. Yep. And then I need to commit this 5. This. Can I pointer? Is it something like this? Yep. Deque. The deque is gonna be harder. Can it be just 2 linked lists? So the deck U. This is a very alarming number. If it's gonna be often deck U, then it's poo poo poo. I'm not sure. So it's gonna be n squared, and then like n squared to this number. Okay, whatever. Let's try to do that. Deck U. Okay, so I'll have this node previous equals head while car next let's call if this size is equal 0, just return null pointer, and then while car next not equal null tail. I'm more inclined to solve it binary. Okay. The deck U should remove the item from I should use linked list, not the built-in containers. I was thinking like maybe double linked list. Why not double linked list? Okay, whatever. So while current next not equal tail, I'll do current equals current next, and then I'm gonna have this prev equals current, and then I'll do prev next gonna be current next, and then self size, or like this size minus minus. Let's check it out. Okay, template. Size. New. Can we do new key like this? Okay, I just push the null value. Null pointer. What? Building. Node, null pointer. Head. Is it like this head, this tail? Can we do T? And then T, new. Okay, let's ask Gemini. I don't know C++ that well. How to eat dummy node key, like head or tail? Okay. Okay, just new node like this. Okay. So T is gonna be on a heap. Okay. Let's do this and see how far we're gonna fly. New node T. So line 20. Head. No matching function. I'll call for the okay. Some kind of node default constructor. Okay, will it work? Test. Okay, okay, line 50. Car next. Deck U. Can I throw? Throw. Throw in C++. Throw in C++. Q is empty. Fifty-six. So I should return the queue. return car as well. Segmentation fault. Okay, let's copy this and figure out what's happening, what's going on. Segmentation fault. Head. Okay, tail. Tail. Head next equals tail. Okay. Get size. Agent size. NQ. NQ. If this size. Tail next. No, tail. Head next. Oh my gosh. Head next equals node. Head next. Node next. Q. Head next equals node. Node next equals head next. So head is in the front. Is it head? Yeah. Head next. So NQ was incorrect. Okay, let's try to run it. Too much time. It was expected. Then how I can EQ ZQ? Can I modify the current class? What they say? Thought that should be double linked list for the efficient. Okay, DQ. So NQ. Head equals new node. Tail is equal head. Oh. Is it something like that's really smart, I guess. So like is it something interleaving nodes? So how to implement linked list with just how to implement the queue with a node and with just a double like single linked list. So NQ head equals new node. We are putting the tail equals I should always include into the head. Okay, I got it. So for the NQ, the head is pointing to the first one. For the InQ, if I include, so the InQ, the tail, I'll add it to the tail, so like here, and when I need to deck you, I'll chop it from the head. And because I have always a tail pointer, I'll be able to add it with the O1 time complexity, like InQ, and I'll be able to deck you from head also with O1. So if I do something like this, head, get size. For the InQ, I will do what was the solution? Okay, head, hell no, not pointer, no pointer, no pointer, no pointer, and then size is equal to 0. Yeah, I got confused by this default pattern. So like if I do InQ, I'll do tail dot next. I'll do the tail next equals new node. Wow. Tail equals tail next. And then here I'm gonna have new node T. Then here new node T. And then head next equals tail. So this is in Q, and then size gonna be incremented. And then for the deck U, I'll do if so head node equals no, node is equal head, and then head is equal head next. This size is decremented, and then return node that, wow, something like this. $47. You know what? Node autumn. Okay. Node T. I don't need to do this. No, not this one. Okay, that's code. Yeah, making too much mistakes. Already a little bit tired. Node, node, like node t, node is equal new node wall, and then node next is equal head, and then node head is equal node. And then size, command the size. And then for the deck here, I'll take wait a second. Still, no, I need to do this thing. No, I need to do this. It was correct. So let me sketch it. Sketch it. Right. So I'm doing this adding elements. So let's say initially I have this structure. I have tail and I have head. And this is null. Whatever. And then I'm adding the A in Q. So to add A, so to add A, what I do tail next. So I'm going with tail, then A, yeah, that's the head, and this dummy note in the middle makes my job harder. So tail dot does it even make a sense to store this tail and head? So let's imagine nothing happens, and then I'll do this A as gonna be tail and head. So A, and this is gonna be head, and that's gonna be tail. And then I do, then in Q and K. So like next time I'm gonna be add B. So I added B, and it's gonna be head and tail, and then I need to see add C. So in QC here will be in QC tail next. So all gonna be tail next, so C, and then tail gonna be this one. So now I need to deck U. This is head, tail, head, tail, this is null. So I need to do deck U. Now check, okay, this head, and this head is equal to next, this side minus minus. This one sounds right. Not head, and then here I'll have this null pointer. Keep it null pointer, and here also null pointer. And then I'll do something like this. In Q, if tail is equal null pointer, then I'm gonna have this tail is equal null pointer, head is equal null pointer. Else, then return. Oh no, tail is gonna be equal node, and head is gonna be equal node. Otherwise, tail next equals node. Tail equals node. Yeah, something like this. $41. Return. still an issue. Tail and head. Head equals what I call why? Okay, I guess I'm getting too tired. Yeah, it's already 2 hours. I've been doing this. What's the problem here? So let's double check. So for the NQ, B and C, NQA, if tail is equal null pointer. Okay. So if size is something like this, size is equal 0, then I'm gonna have this. Yep. Or I could have just did like this head and then here like avoid it. Okay, let's add this to my library. Library here. Okay, and commit. Git commit. Sunday Structy learning session push. Okay, so let's watch some of this video for the linked list. We have here remove node. Okay, approach.
Hey programmers, Alvin here. Right now I want to go over the approach we can use for this remove node problem. So in this problem, we're going to take in a linked list and also a target value. What we want to do is remove the node in the linked list with the given target value. So in this particular example, I do want to remove this C node. And I need to perform this removal in place, meaning I should actually mutate the existing nodes, resulting in the list of just ABD. In the context of my function, I should return the resulting head of the list. So I'm going to go about solving this one. Well, the important thing to notice is, although I want to remove the node C, to actually perform that removal, I need to actually make a change to node B, right? Node B needs to reroute its next pointer. And that's an important concept for this problem. In other words, I need this operation to take place. I need to reroute B's pointer to point to actually the D node. And this would effectively remove C from the resulting linked list, just like this. So it's pretty clear to me that to tackle this one, we're going to need 2 pointers. We're going to have our current pointer. We also need to track our previous. And then as I traverse through my linked list, at some point, I can see that my current value of C matches my target. So at this point, I would have access to the node before the target I need to remove, but I will also have access to the node after the target I want to remove by simply stating current.next. And the effect I want to have now is to remove current. So what I can do is take previous is next, in other words, B's next, and point it to current's next, basically rerouting over the current node. This would effectively delete it from the linked list. So that actually seems like a pretty straightforward strategy and one we've seen before, tracking our previous node as well as our current node. But one thing we should be aware of is any edge cases here. Very common for linked lists. What happens when we're at the tail? In other words, what if someone asks you to remove the very last node of the linked list? It's worth checking to see if this algorithm performs that operation as well. So let's reset. Let's say that now I wanted to delete my target of D. And so if I step through the same algorithm, I'm going to track my previous and current, and I keep traversing until my current's value is equal to the target value, which would be at this point. Behind the scenes, I know that D does have a next, and that next just points to null. So current.next would be null. And if I followed the same steps as before, I would take my previous's next pointer and point it to current.next, basically foregoing the current node of D. And that actually would effectively remove it from my linked list. So it's clear to me that this algorithm would actually pass removing the very tail of a linked list. But what would happen if someone asked me to remove the first node, the head of the linked list? We should step through that scenario as well. So we'll reset to our original list of A, B, C, D, and let's say now my target was A. If I follow the same algorithm, something goes wrong here, right? I'm at the point where my current matches my target, but there's no previous to reroute. And so this is actually going to be a special scenario. To do a deletion at the very head of our linked list, we should really just return head.next, turning everything after the initial head. We're going to have to handle that case explicitly, removing at the head of our linked list. That being said, in terms of the complexity of this general algorithm, if we say that n is a number of nodes, we're going to have O of n time for just traversing through the linked list until we find our target to remove. And we also only use a constant amount of space because we're not storing too many things, really just some classic pointer variables. With that, I want you to give this algorithm a shot, try to code it on your own. If you get stuck, you can find me in the walkthrough videos. I'll see you there.
Okay, I already coded that because I got impatient. Let's think if I wanna do that in Swift. I better do the next one in Swift. Insert node. That sounds like more interesting and fun. So if I do insert node, that's a new empty file. Insert node. Paste it. That node. And then I wanna do new empty file. Insert node. Tests. And I want to check the tests I have here. So I have this tests, insert node tests. Okay. Then here, what's that? I am confused. Third notebook tests, okay. Let's copy this. insert node, and then cut it, insert node here, insert node, okay, insert node, oh no, insert node, and then here insert node, here insert node, here insert node, and then linked list values. So let's assume we are inserting, let's run first this test, and then it's gonna be fail. Yep. And then I'll add another test like empty A, B, B, C, empty list. What about empty list here? So let's say we have node node is equal A is equal node string nil, and then A, and then it should return Z. Let's insert foo bar, and that's gonna be 0, 4, 0, 4, and I wanna insert a node. Okay, so I'll do this. Let's say node let like var dummy equals node foo bar, and then dummy next gonna be equals head, and then I'm gonna do this var counter equals 0 while counter less than index. I'm gonna have this var node is equal dummy, node is equal node dot next, and then this one so this one is going to be node key optional, and then string, okay, as you wish, string. So dummy for bar, dummy next head, node is called dummy, so no current equal counter plus plus equal 1, and then let's call var pref equal node string equals dummy equals head equals pref. So equals dummy. Okay, and then here node pref.next equals so here our new node equals node and then value, and then pref next equals new node, and new node next is equal node, and then I want to return dummy next. Call pref node here. Node Then current node next. And then prev node equals current node. Prev node next equals new node next equals node. Okay, that sounds right now. So let's run it. Optional. Okay. What is this? Okay, so the tests are green now. Insert node. It's a little bit verbose here. Have I solved it the same way here? Dummy node, dummy next, head, previous counter. Feel like should be. Okay, it's identical. Variable non-mutated apply. Apply. Okay. Was non-mutated apply. Are you going right now? That's what I wanna go.
Yeah, I tried even driving her with Starbucks. But
Okay, I'm
she
gonna wrap
said
up.
she doesn't want to.
That's it.